So, what if I told you that you could listen to a secret song that every single molecule sings? A totally unique tune that reveals its exact shape, its identity, everything. Well, today we're going to decode the technology that does just that. It's called NMR spectroscopy. But before we dive into the how, let's just stop and think about the what for a second. I mean, we can all see the world around us, right? A chair, a tree. But how do scientists actually see the precise three-dimensional shape of a molecule? We're talking about something so incredibly small, it makes a single grain of sand look like a mountain range. All right, here's how we're going to break it all down. We'll start with something you've probably heard of, an MRI. Then we're going to shrink way, way down to see how atoms dance. After that, we'll look at how the machine actually listens in, how we translate those signals into a structure, and finally, why this all matters in our everyday world. Okay, let's kick things off with an analogy that makes this whole thing a lot easier to grasp. If you've ever had an MRI scan or know someone who has, you're already halfway there. NMR is, for all intents and purposes, an MRI, but instead of looking at your body, it's looking at a single molecule. So, what does NMR actually stand for? It's nuclear magnetic resonance. Now, I know that sounds super technical and a little intimidating, but the core idea is actually pretty straightforward. We're using magnetism to poke and prod the very heart of atoms, their nuclei, to figure out what they look like. So yeah, let's just cut through all the jargon for a second. What's the bottom line? What are we really doing here? It's all about one thing: creating a precise 3D map of a molecule. It's how we make the invisible, well, visible. And this chart really spells out the difference, right? An MRI is looking at the big picture, your tissues, your organs, on a scale of millimeters. NMR, on the other hand, zooms in, way, way in, down to the atomic level. But here's the cool part. Both of them use the exact same fundamental physics, just pointed at vastly different things. So how on earth does this technology actually work? Well, it all comes down to some really cool physics. Deep inside every atom, there's this kind of secret dance going on, and that's the key to everything. Here is the one idea you really need to get. The nucleus of certain atoms, like hydrogen, for example, isn't just sitting still. It's constantly spinning. Just imagine a tiny microscopic toy top spinning on its axis. Now, this spin is absolutely crucial. You see, because the nucleus has a charge, that spinning motion generates a tiny magnetic field. So what you end up with is that every single one of these nuclei acts like a miniature compass needle. Billions and billions of them, all inside your sample. Okay, so we've got all these tiny spinning compass needles floating around. How do we get any useful information out of them? Well, we build a very powerful, very sensitive machine that's designed to listen to their unique atomic song. And the whole process basically happens in 4 steps. First, we put the sample inside a huge, powerful magnet, which forces all those little compass needles to line up. Step 2, we hit them with a quick pulse of radio waves, which knocks them all out of alignment. Third, they naturally start to wobble back into place. Scientists call this relaxation, and as they do, they release a tiny burst of energy. And that brings us to step 4. The machine listens for that energy. And that little signal of energy, that's the magic right there. It has a very specific frequency, and it acts like a completely unique fingerprint. It's determined by what kind of atom it is and who its neighbors are. It's basically a little signal that screams, "Hey, I'm a hydrogen atom, and I'm standing next to these other guys." Now, just getting these signals is only half the battle. The real genius is in the translation. How do scientists take this huge chorus of different atomic songs and turn it into a single, coherent 3D picture of a molecule? Here's the secret sauce. The song an atom sings actually changes depending on who its neighbors are. You see, those neighboring atoms create their own little magnetic fields, and that subtly changes the pitch of the song. So a hydrogen next to an oxygen will have a slightly different frequency than a hydrogen next to a carbon. So by carefully analyzing all these tiny shifts in frequency, scientists can build a complete profile. They can figure out the type of atom, they can pinpoint its exact location, they can tell which other atoms it's bonded to, and they can even figure out the 3D arrangement of the whole thing. A scientist then takes all of these little clues and, with the help of some seriously powerful computers, pieces them all together. It's like solving the world's most complex, invisible jigsaw puzzle. And the final picture? It's a perfect 3D model of the molecule.
This is all incredibly cool science, right? But what's the real-world payoff? I mean, why does making this molecular map actually matter to any of us? Well, it turns out it matters almost everywhere. In medicine, if you know the exact 3D shape of a protein that causes a disease, you can design a drug that fits into it perfectly, like a key in a lock. In food science, NMR can spot counterfeit olive oil just by looking at its molecular fingerprint. It's used for medical diagnoses, for creating new materials. The applications are just enormous.
I love this quote because it just nails it. NMR isn't just a big machine. It's a tool that lets us have a conversation with the molecular world. We can literally ask a molecule, "What are you? What are you doing?" and actually get an answer. And that brings us to the single most important takeaway from all of this. In chemistry, in biology, in life, a molecule's shape determines what it does. Its structure is its function. And by finally being able to see that shape with NMR, we can begin to understand and maybe even control what it does. The language of our world, everything from our health and the diseases we fight to the very materials we build with, it's all written in the shape of molecules. And NMR is our translator. It lets us read that language for the very first time. So now that we can finally listen in, the only question is, what secrets are we going to hear next?